This is the 15th workshop held at Johns Hopkins. There were two previous ones held at Rutgers. We started in 1995 and have gone on like this ever since. The shape of the workshop is a little bit different than it started out as. It was strictly on speech recognition, and now it is, at least its aim is on speech recognition and natural language processing, including machine translation. And we take suggestions from everywhere, actually, on any related subject. When I say related, I mean subjects that we are interested in. All right? And that, by definition, is related. It's like, what is electrical engineering? Electrical engineering is what electrical engineers do. And, you know, it doesn't have to have anything to do with electricity or etc. And that's how the fields grow and flourish. Anyhow, we started out, as every year, with a conference in November, the planning session, where we, for which we solicited proposals for work in this workshop, and we got 15 proposals, and we invited, I don't know, people from maybe 12 of these we deemed to be appropriate, and we invited.
I think these were the 15 that were invited.
I see, so we got more.
There were a couple.
So 15 were invited, and we invited people, proponents of these 15, plus some experts from both government and academia to judge what's going on. And we went on for about 3 days. That means starting with a session on Monday evening, and then going through Saturday and through Sunday lunch. And from there emerged 3 proposals or 3 tasks that we agreed would be good to work on this summer. And you know what these 3 proposals are, namely they are the ones that whose teams are present. There was dialectal Chinese speech recognition, joint visual text modeling, and landmark-based speech recognition. Actually, the Chinese speech recognition was a shoo-in. We already decided on it a year earlier, but because of the SARS outbreak and impossibility of meeting in China, or Chinese people coming here and meeting with us, we delayed it by 1 year. Now this year it was somewhat damaged too, because certain people, I mean the original head of the team, Thomas Zheng, could not get a visa. I understand from Sanjeev that he got a visa today.
This morning.
And this morning, so he will presumably, if he gets a plane, come here later.
The visa doesn't mean they'll let him into the US. Technically speaking, they could still send him back from the port of entry.
You heard it from the whole. So we will wait with breath abated to see what's happening and whether he will show up or not. We have another casualty in joint visual text modeling, namely Harriet, who was going to be the head of the team, got carpal tunnel syndrome, and I understand is enjoying a vacation in London, presumably doing nothing with her hands. We invited her to do things here with her brain, but I don't know, she didn't think that was We did. I mean, we promised her slaves, and people would be typing and carrying and all that. No, this is literally true, right?
No, but I think she admits to being an obsessive compulsive type person.
I see. Well, we would have also been willing to tie her hands, force her to go to sleep at the right time, etc. All to no avail. We couldn't. I mean, we would have had to send some representative to IBM to get. Anyway, these are the 3 teams, and I'm not going to read what they're going to be doing because their representatives will be talking here to tell you what it is that they intend to do. And at the end of the workshop, we will see to what extent they did what they promised they're going to do. They not only promised it to us, they promised it to themselves. So, here is some information about who it is that's here. We think we'll have 33 total participants. Does that include Harriet?
No.
I see. So maybe we, okay. Anyway, our teams are usually made of 4 senior researchers, 2 graduate students, and 2 undergraduate students. And this is what it turns out to be. Some people are added, some people are subtracted. The undergraduate students are selected in a national search, and the people who are here know what the situation is. I think this year we had something like 80 applicants. Is this right? And we have selected 6 students, so they are in some sense the end of our applicants. All right. Our experience with the undergraduate students is excellent, and they perform as well as the graduate students who are in fact in the field. And as you know, there was a pre-workshop that went on for 2 weeks preceding this week, and we tried to acquaint those who were not familiar with our field with the field through various lectures and tests and laboratory exercises and what have you. Finally, I want to say something what you can expect. This is how a week looks. Tonight there's going to be an opening picnic in the lawn behind Clark Hall, and if you don't know where Clark Hall is, somebody will show it to you. I think it's not going to rain, so it's truly is going to be outside a picnic. On Wednesdays we have seminars in the morning by distinguished speakers, not necessarily completely related to the subjects here, although this week we have Mary Harper, who is related to the subject here. And then we have a common lunch that's not mentioned here on Wednesdays, where everybody gets together and it's a buffet lunch. And then there are team updates. On Thursday, we usually go to dinner together. That's the attendance is voluntary, and we don't pay for it. There are undergraduate brown bag lunches on Thursday, where the faculty here, us, Sanjeev and I, and the team leaders get together with the undergraduate students to see how they're doing, and they tell us about what they're doing. And finally, on Friday afternoons, we have an afternoon social. Another thing is there is a steering committee consisting of next, I think, we have Dean Dunnett, Dean of Engineering, W, Associate Dean of Research in the Viking School of Engineering, who's going to say something.
I want to welcome you all here on behalf of the school. And one of the things that is evident that is a high priority for us is the diversity of the group. This group of people, I hope you get a picture sometime during the conference, because this is a really fabulously diverse group of people. And the other thing that I think is very important is the whole structure of working in teams. And this is something that engineers traditionally in engineering education have not done. Engineering education has been solve your homework problems and take a test and solve. But the reality of engineering work outside of the university is that it's all teamwork based, and it's very refreshing to see that kind of an environment permeate into the university and become a part of the culture here. Finally, I'd like to comment on this program. This is a really remarkable endeavor that Fred has organized and was at Rutgers before CLSP existed here. But this notion of bringing people together to work on substantial problems in a team collaborative environment where you involve students, this is a wonderful thing. And the school and the university are strongly behind this. We hope that this, I know it's a huge amount of work for CLSP to put this on every year. We really hope that it continues, and we hope that you enjoy your participation in the program. Thank you very much.
Thank you. Now, We were hoping for the workshop sponsors to come here, and every year they came. But this year they don't seem to be here, so we'll skip. There are all sorts of activities going on in NSF, for instance, Maria. Never mind. Everybody who we invited said they are terribly ungrateful that they are not talking. So what's next? Next is...
I'll give you a quick overview of what we've been doing in the recent past,
yes.
and then we'll continue. Just give me a minute while the display warms up.
We can display, see what's on your mind.
Unfortunately, my computer is giving me trouble this morning, so...
So Apple never gives no such trouble.
Well, it usually doesn't. This is just
I think it has to be blamed on something else but the computer.
Okay, well, I apologize for this. Let's see if we can get this to behave. Finally. Okay. Well, I just wanted to sort of remind people that what we do in these 6-8 weeks often gets called the summer workshop. But if you're at CLSP, this doesn't feel like a summer event. It really feels like a whole year-round event. And here's sort of a well, I guess it's a desired timing of things. Things don't always happen on this clock, but this is roughly how they happen. And basically, you're here now, and through July and August, you'll do your workshop. But really, as soon as this gets over, even before it gets over, there will be a call out for proposals for next year's workshop. The deadlines are sometime in October, and we have to screen. We get all sorts of proposals. Most of them are good, but some of them are really off the wall. And then you have to decide whether this is a serious research proposal or just some crazy guy or girl proposing something. And then we usually keep all of it, even if they sound crazy. And then only very few get thrown out. Then in November, as Fred said, we meet and we try to review these proposals in an objective way. We select team leaders. Then we sort of tell NSF and DARPA and NSA that this is what we would like to work on. And they tell us in December that they'll give us the money. Usually the money shows up in January or February. In the meantime, we finalize all the senior members of the team. That's typically over Christmas. Then by February, we sort of tell the team leaders to tell us who the grad students are going to be. In the meantime, we've been advertising for undergrads, and we get lots of applications. We usually choose them in March. And then April, May, and June, the teams usually have at least a couple of team meetings where everybody gets together and tries to plan what to actually do in the summer. And then we have the 2-week pre-workshop, which is now being called the summer school by others, and then we go on and do the actual workshop. So it really takes a lot of effort all through the year, and so like, for people outside, it's a summer activity. For us, it's something that really takes up about maybe a quarter of Sue and Laura's time all through the year and so on. Right. So what's the team selection process? So we had an open call, and this year actually we started fairly early. I think we issued the call for proposals at ACL. Jason took some flyers, I think, Chris Meisner, on July 7th. And then we usually advertise electronically to hundreds of people on mailing lists and so on and so forth. And usually we then tell our program managers at DARPA and NSF and NSA to arm twist their PIs to send in good proposals, and that's usually where some of the team. And we screened and got rid of a couple of them, and then there were 15 viable proposals, as Fred mentioned. And then we had this 2-day review panel. I say 2 because we started on like in the 7th afternoon and ended on 9th afternoon, so it's really 2. And we basically get the authors themselves to come and defend their proposals. We have some of their peers who try and sort of talk them into either improving it or perhaps refocusing it somewhere where it's more interesting, or sometimes just saying this is not a good proposal. And then also JHU faculty show up there to sort of moderate the whole event, but really it's run by other people in the community. And we then vote. It's a single transferable voting system. We have a fairly well-documented program that makes sure people don't have to play any games, that they can vote their conscience and the vote comes out right. And this time we ended up selecting the 2 highest rated proposals from this pool and one proposal which had been postponed, which had won a similar competition last year, but had been postponed because of SARS, as Fred said. So what were the proposals? Here they are. It's a long list. I don't necessarily want you to read all of them, but just a quick summary. Out of the 15 that are here, 7 are on speech recognition or speech science. So this time it was a fairly large chunk of the total. 5 are on machine translation and machine translation related research. That's 7 and 5. There are 2 on information retrieval or search. One is this spoken document search and the other one's the joint visual text modeling. And there was one sort of slightly different, interesting proposal on text watermarking. So there were 15 of them. People talked, debated, so on and so forth. And in the end, we selected the 2 or 3 that I mentioned. So who are these people who are doing all the debating? Well, these are the names. Again, the names are not very important. You can see many of the authors of the proposals are in there. Some past team leaders are in there to sort of help guide the selection process and tell the participants what it is they're getting into. And if you look at the breakdown, about 15% are government people, a third are from industry, another third or a little more from outside Hopkins, but otherwise academic, and then about a sixth of them are Hopkins faculty. So this is the way the meeting is run, and the teams that were selected were landmark-based speech recognition. It's led by Mark Hasegawa-Johnson. We have, I think, 5 other senior people, 4 grad students, and a couple of undergrads, Emily and Tom. So these are the 2. The next team is joint visual text modeling. This is led by Giri Iyengar of IBM. There are another 3 or 4 senior people there, 4 grad students, and the undergrads are Desislava over there and Matt Krause. And then finally, the team from last year, which is back now, dialectal mandarin speech recognition. So what Fred didn't mention is that Richard stepped forward to lead the team because there was so much uncertainty about Thomas's participation. And then this team also has a couple of other senior members, and then 4 grad students, and Philip and Dave are the undergrads. All right. So these are the 3 teams. Then the other activity that we went through is some students put them in one place and paste them through all the different components that go into what one would call human language technologies. They talk about speech recognition. DARPA speak for that as STT, speech to text. They talk about detection, meaning retrieving documents. They talk about extracting information from documents, summarizing documents, translating documents from one language to the other. And a brief history of how this started. We used to have senior people and undergrad and grad students in the workshop, and starting in '98, we started including undergrads. And then we looked at them and said, gosh, these people don't have any idea what they're doing. Let's educate them quickly. So this was sort of how we started these tutorials. And then people from DoD said, hey, this is a nice quick review of everything, so why don't we send some people over there? And then NAACL said, NAACL is this Society of Czech Students. They said, oh, don't worry, we'll pay for our students. Fine. So before you knew it, we have 30 plus people, and it's become an annual event with a life of its own. And for example, this year, we had this agenda. So on the first day, we had Bob Moore from Microsoft, Mark Johnson from Brown talk about NLP. Jason had them build parsers in a competitive way in the lab. Then for information extraction, we had Lance Ramshaw, Andrew McCallum, and then Radu Florian from IBM, again, had them build named entity taggers. For detection, we had Nick Belkin, who's the head of the library science department at Rutgers, Tagore, Gina Lvov, had them build IR systems. Translation, we got Franz Ochs, Stefan Vogel, these are some of the leading researchers in the field these days, and then David Jarowski and Charles Schaefer organized a lab for them, where again they used tools to build machine translation systems. We had summarization, and you can see the rest of it. There was a day, or more like a day and a half on speech recognition. They talked about, and then of course we had some time spent dedicated to each of the teams, so Mark and his team introduced them to various kinds of acoustic landmarks and how they could be used for recognition. We had a day on, I guess, image annotation, where they talked about how to sort of analyze images for content based on the text that's around them, and also you can sort of learn the correlation between captions and images. So these are the 2 weeks, and all the students have gone through it, and hopefully they're the better for it. Time will tell. Finally, what's in store for the rest of the 6 weeks? This is roughly what it looks like. We are up there on July 6th. This is the opening day. And the dates that you have to look out for are August 16, 17. That's when we have a day and a half of presentations. And in between, there's a lot of other activity, but most of the workshop is quite unstructured. So every Wednesday, we have a plenary speaker. This would be at 10:30 or so in the morning, followed by lunch, followed by a team update. And 4 of the 6 speakers are set. Mary Harper from Purdue, David Forsett from Berkeley, Ken Stevens from MIT, Dave Roy also from MIT. And then Thursdays, we have the lunch with the undergrads and the group dinner. Every Friday is a town hall meeting, so if you have any problems or any grumblings about the workshop, this is when you make noise and say, oh, the air conditioning is broken, or oh, why don't we have Oreo cookies in the afternoon, and so on. And the other thing is, for more serious matters, there is a steering committee meeting where the team leaders meet with Fred, and if there are any issues to be resolved organizationally, we do it at that time. And otherwise, there's a lot of unstructured time where people will do research, and I hope you enjoy your time. One thing I would say is take time to meet with people from other teams, because it's a really good opportunity to kind of learn other things that people are doing. So for example, when you go out for lunch or dinner, try to hook up with people from other teams so that you get to talk about things other than what you're doing. And finally, are really open to the public. So if you know people in the area, or if some of your colleagues in your home institution want to attend, especially the final day's presentation, August 16, 17, extend contact soon, and we'll be able to point them. And that's pretty much what's in store. Oh, questions, comments, jokes? Okay, thanks.
Well, maybe I'll put out the program slide. So we're at the end of the first section, and we're doing much too well. I don't know if we want to take a break or not, maybe not. So why don't you, Richard, tell us what you're about.
This is probably not going to help much, these speakers, but see there's no sound possibly there.
Over here, if you could put it
No, I don't have a thingy though, I don't have anything to connect to. If you have the cable open with it. Sorry, I didn't want to do that. Okay, I'm doing very well here. But we're ahead of time, right, Fred?
Yes, we are.
You're doing better than me.
So talk about it.
Marginally. Okay, so this thing unhibernates. So, as you've heard, the gods have not exactly been smiling on this project, but here we are. So very graciously asked me to take over as team leader after it was found that Thomas didn't get his visa, and apparently he does have his visa, so hopefully he will be here. So let me just give one little bit of background here. We're talking about Chinese dialect recognition, or dialect or accented recognition. I want to just make a couple of things clear. You'll hear the term Chinese dialects used to refer to languages like Cantonese and Shanghainese and so on and so forth. The Chinese term for that is fangyan, so literally aerial language or something like that. Now, really, these dialects are really separate languages. They're only considered to be dialects of the same language really for more political reasons than linguistic reasons. And there's a common misconception about Chinese, which is that the Chinese write the same but speak differently. Now, actually, this is true. So why is it a misconception? Well, it's a misconception in the sense that, well, the reason it's true is kind of for trivial reasons. That the reason that everybody writes the same is because when you learn to write in China, what you're learning is in effect a standard language. So you go to school and you learn the standard language, which is some variant of what we'll be calling Putonghua. Basically, the written version of that is what you learn when you learn to write and read in China. So what we're actually going to be doing here is not the dialects in this top sense, but Putonghua, that is the standard so-called ordinary language, or what's often called standard Mandarin. Okay. As spoken by people whose native language is something other than Mandarin, in this particular case, people from Shanghai. So they speak their native language would be an Wu language of some kind, mostly Shanghainese. Some of them are possibly from around Shanghai and wouldn't speak exactly Shanghainese, but it'll be some kind of Wu dialect. But they're speaking Mandarin because, to varying degrees, they've learned Mandarin in school, okay, or they've learned it as from day-to-day use. Just to give you an idea, now this is where the speakers come in, I just want to give you an idea of what the differences we're talking about are. So what I'll play for you are two kinds of differences. First of all, the difference between Putonghua, the standard Mandarin, and the Wu dialect, okay, so the actual Shanghainese speech. And then I'll give you a distinction between Putonghua as it's spoken by a native speaker of Mandarin and as it's spoken by somebody who's not a native speaker, who's a native speaker of Wu dialect. So hopefully this will be audible to people in the back.
有1200多个学生。
Okay, so that's Mandarin, okay? Now, even if you don't speak Chinese, hopefully this should sound somewhat different. Where are you going?
有1200多个学生。
So that sounds, it's a different language, okay? You can probably hear a few words in common. By the way, I don't speak Shanghainese. I got this off the web. I hope this is Shanghainese. It said it was. But you never can trust these things. Okay, so now you're going to hear the difference between Putonghua is, again, spoken by a native speaker. And for those of you who are native speakers of Chinese, you will undoubtedly have detected that the particular speaker in question comes from Taiwan. Okay, and she happened to be the one I had available. But in any case, she's a native speaker of Mandarin. And then the next one will be spoken by somebody who comes from Shanghai as a native speaker of Wu dialect.
花是龙花是怎么带来的，对吧？我看了一篇是常说的，就是啊。
Okay, so she was basically imitating to the best that she could the manner of speaking of the native speaker who you'll hear now. Sorry, the non-native speaker.
龙花是怎么带来的，对吧？但是我看了一篇是常说的，就是啊。
Now, for people who don't speak Chinese, that may be harder to detect the difference there, but there are some very clear identifying features. In particular, there's this difference that we'll see later on between the pronunciation of certain consonants, like sh becomes s, and that kind of thing, a very characteristic kind of feature. Okay, so what are the project goals? So the basic goals are to do dialect recognition, or that is recognition of this accented Mandarin, or accented Putonghua, I should say. We want to model the obvious kinds of things that you would need to model, in particular phonetic variability, possibly lexical variability, although we'll probably focus less on that, and pronunciation, differences in pronunciation. And in particular, since we're assuming that we don't have a lot of data, and in fact we don't actually have a lot of training data, we don't have enough data to be able to train a dialect or accented specific recognizer. We're particularly going to be looking at methods to adapt an existing recognizer for Putonghua to particular regional dialects. Okay, so that's a standard kind of thing to want to do these days. Let me say a little bit about the data collection. So we actually have a database of 11 hours of 100 speakers with various degrees of accents. They were collected in, I guess, a couple of different locations around Shanghai. They were coded for things like gender, obviously, age. It turns out the age and the next factor, education, perhaps not surprisingly, quite important. The level of Putonghua, that is, how well they seem to know the language, and then fluency, which is arguably different. I mean, you can be very fluent and still not know it very well. The set of data was actually in two parts. We had red speech, and the reason this is kind of fainted out is because even though we have this data, we're not going to probably be making too much use of this in the workshop, although we may make some use of it. Basically, the red speech was just having people read sentences that were written in standard Chinese. And in a few cases, there's a few hundred words of Shanghainese style words which are kind of inserted into the text to have them read things which were based on Shanghai vocabulary. As I say, we're not really going to be using that very much. The main set that we're going to be looking at, because it's more interesting and arguably more difficult, is spontaneous speech, and this was done in conversations with a native speaker of Putonghua, so somebody was conversing with these people and basically on particular subjects which they got to choose. So they could be sports, policy, economy, entertainment, lifestyles, or technology. Now, I listened to actually all 100 of these conversations over the last couple of weeks just to see what they were like, and one of the things I noticed, I'm not sure why this is the case, but the policy and economy, all of the people who spoke about that, as far as I can tell, were men. The women never picked that topic. I don't know why. It just seemed to work out that way. We also had some data from Beijing speakers just to give examples of standard Beijing Mandarin. So we can use that kind of as a baseline, as it were. The other thing that was developed was a 50K word electronic dictionary, where each word would have the standard pronunciation as it would occur in standard Chinese, and also Wu pronunciation. The pronunciation that a word would have in the Wu dialect, not in the accented Putonghua of the speakers. So, if there's any underlying influence of the dialect, then this would be useful data. Okay. I won't bore you with the details of the data set division, except to say that we've divided the data into a dev train, a dev test, and a test set, roughly 80, 10, 10 percentages. We split the data. I mean, there are too many factors to really split fairly according to all of the factors. So we looked at age, basically younger and older, education level, higher and lower, and the Putonghua level. We didn't explicitly split for gender, but it roughly worked out that we had a 50% male and female in each set. So the baseline system, we do have a baseline, just to see how well a standard recognizer would do on these data. Again, I won't bore you with the details. Basically, we took a standard Chinese acoustic model for spontaneous speech. Actually, we got it from here. And we didn't have a language model, really. I mean, we basically just assumed a simple syllable concatenation model, and we were actually scoring on the basis of syllables correct. So, there's most of the work, as it were, is being done by the acoustic model. Now, if you compare the two sets, if you compare the two sets, we did this on Hub 4. So this is basically new style Chinese speech, standard Chinese. This score is, of course, lower than what you would have if you'd done this with a language model. But the interesting point is to compare this with this, down here. Obviously, we're doing it significantly worse on the just using a standard recognizer off the shelf for the Wu dialectal test set. Okay, let me say a little bit about some of the linguistic details of this. So some work that Dan Jurasky and one of his students, Rebecca Starr, did was to look at some of the changes, sort of from a more sociolinguistic point of view, that you find in these speakers. Now, what they chose to look at was this change that I alluded to earlier, the sh and j changes to s and z, and we'll call this fronting. Now they also looked in the other direction. You get cases where things which should be "se" in, say, the standard language show up as "sh" and they speak, and that's what we would call hypercorrection. So, they don't know how to distinguish "se" and "sh," so they will often make them, they'll often hypercorrect by doing the wrong thing. But right now we'll just talk about the first one. They collected a bunch of instances of these in the corpus. In fact, they had about nearly 20,000 examples, and coded these by different factors: age, gender, education, and so on and so forth, and showed the various of these factors are important, but in particular, one of the main things that showed up was that age and education are really the best predictors of whether or not you get a standard pronunciation for sh and j. Okay, in particular, younger speakers, and they tend to be the better educated speakers too, tend to be more standard. Okay, but the other thing is to notice that you get anywhere between 15 and 100% standard pronunciation depending upon the speaker. Okay, so it's not it's not that there's sort of one way of saying it among all these speakers. There's a huge range. Okay, so this just shows that. Basically, what you see here is, okay, on the vertical axis is the percentage of fronting, so the lower it is, the more standard they are. Okay. On the horizontal axis, you have the age, so 25 to 30, 31 to 35, and so on and so forth. And as you can see, the older the people get, then the less standard they are. There's also a difference between spontaneous and read speech. Not surprising, people tend to be more standard when they're reading. Okay. So what do we conclude from this? Well, one of the things that seems to follow from this is that you need speaker-specific, or more realistically, speaker-type-specific adaptation. Basically, you can't assume there's simply a U dialect dictionary, U accent dictionary. You actually need to have some kind of measure of accent severity, for lack of a better term. And have some way of actually predicting that based on some small amount of data, and then sort of adapting according to what you think the speaker is. So what we're going to be looking at is three kinds of adaptation. Okay, acoustic model adaptation, lexicon adaptation, or you call it pronunciation modeling, and I'll say a little bit about language modeling. We don't expect that that's going to have much importance, at least for the data that we have. So for acoustic modeling, the basic point is obviously to come up with acoustic models which are appropriate for the speakers that we have. And let me actually skip over this slide and go to this one here. The basic idea is, as I sort of intimated in the previous slides, we'd like to try to cluster speakers into accent severity types. Okay, so you're going to have speakers who are more heavily accented, speakers who are less heavily accented, and you'd like to be able to do that on the basis of a bunch of different kinds of factors. Once you know for a given test speaker which type that he belongs to, he or she belongs to, then you want to, as it were, import acoustic models that are appropriate for that particular kind of speaker. A second idea is to increase the kinds of features that we're using in acoustic model adaptation. I won't say much about that here. Hopefully we'll develop this over the summer. And then the third idea is, it could be that even in sort of so-called standard put-on-voix sets, there are speakers who nonetheless sort of fall into categories which are similar to what we have in particular U-accented speech. And so, one idea would be to actually mine those kinds of sets for data that could be useful for adapting acoustic models. Let me say something about lexicon adaptation. So everybody knows the standard approach, right? It's basically rule-driven. The rules could be handwritten. They could be derived by some kind of learning algorithm, such as CART. But basically, the idea is you come up with a set of rules. You use some training data to associate probabilities with those rules, and then you use the resulting rules or the resulting lexicons, which have been annotated with probabilities at test time. Now, to be fair, this initially had quite a bit of success when Mike Riley and others did this, say 10, 15 years ago. This was quite successful, but there's a number of reasons why over the years the importance of doing it, of that particular approach, has sort of waned, as it were. So one is that when he was originally doing this work, people were mostly not using triphone models in acoustic modeling. So it turned out that there was a big gain when you moved to a wider context. And the other thing is that adaptation by things like MLLR becomes, ends up having a significant amount of importance. such that if you do things like MLR and then you do you know, adaptation of pronunciations on top of that, you often get no or very little gain. Okay. Now, you know, something seems intuitively slightly wrong about that. You still think that there ought to be some gain that could be got out of doing better pronunciation modeling. So the idea here then is, rather than trying to you know, have again a model that's appropriate for all accented speech, you want to do something which is maybe more specific to a given speaker. And so the idea again would be to have some ways of detecting appropriate strengths of accent designations, and then using that information to, as it were, adapt the lexicon to that particular speaker. So that's the basic idea. As I said before, language model adaptation is something we plan to do. We don't expect to gain much by doing this, and for the simple reason that there really isn't, in the spontaneous speech, there really isn't very much that you could argue is influenced by the speaker's underlying Wu dialect. It's pretty much standard Mandarin. There may be a few things in there. There's certainly, you know, they tend to use final particles at the end of sentences, which are more characteristic, perhaps, of Wu than they would be of standard Putonghua. But there's not a huge difference. It's not as if you see massive syntactic reorganizations. Okay. So we don't expect there to be much gain. However, we will do some of the standard map adaptation stuff using the data that we have. Okay, so to summarize, we're going to mainly focus on two areas. We're going to be looking at acoustic modeling, and we're going to be looking at lexicon adaptation and pronunciation modeling. And the themes are going to be, apart from adaptation, in particular, the idea that you want to have some way of clustering a new speaker into a given known type, and then adapting both the acoustic models and the lexicon models to that particular type of speaker, and hopefully thereby actually show that you can do better than you would if you, for example, had something which was appropriate for the whole Wu accent. Okay, so that's basically it.
I just want to get this straight here. Please for myself. You might have it on straight. So sometimes you say Chinese, sometimes you say Mandarin. Anytime you say Chinese, you mean Mandarin. Is this true?
Yeah, it's close to being true. I was a little. It's hard to keep all these terms straight. Okay, so the terms we have to keep are, you know, Putonghua, which is, I realize, a bit of a mouthful, but basically it's the standard. It's the common term for the standard language. Okay, so that's really
standard Mandarin.
Well, okay, so Mandarin. Okay. Since you raised the question, okay, so Mandarin. Properly speaking, Mandarin is a group of dialects. Okay, Standard Mandarin is the language, is the national language. Okay, so that's what I mean by Putonghua. Okay.
Okay.
Mandarin. The problem is
Cantonese, for instance, and that's different.
I'm sorry.
But there is Cantonese.
Yeah, that's different.
And that's different.
That's clearly different.
And every Cantonese worth his whatever soul will learn Mandarin in order not to be.
Yeah, I mean most Cantonese speakers do speak Mandarin, but again,
so the whole nation, the educated people of the whole nation would speak Mandarin.
Yes, I mean that's a fair statement. I mean you can't really be educated. Now, of course, that's not true in Hong Kong necessarily, but in mainland China.
Yes.
Right.
Now, Putonghua
yeah.
is going to be the manner in which they express Mandarin. You know, the writing is Mandarin, and there is no Putonghua writing. Is this correct?
Okay, so the written language is based on standard Mandarin. Okay? It's a written version. Obviously it's not the same as the spoken version, but it is based on the standard language. So when you go to school to learn to read and write in China, you're learning that.
Yes.
And if your native language is not Mandarin, you will have to learn things which are not native to you.
Right. Okay, and the Wu people are who? No pun intended.
You don't want the standard joke? Okay. Right, so the Wu dialect is, well, I'll just go back to the map here.
Yeah, exactly.
Okay, so the Wu dialect is what I've actually circled in red, or outlined in red here. It's spoken mostly in Zhejiang province,
So that's a Wu dialect of Mandarin.
No, it's Wu dialect of Chinese. It's different. It's a different language. So it is not mutually intelligible with Mandarin. If you speak Mandarin and you don't know anything about Wu dialect, you will not be able to understand it.
So why do you use the word dialect? Why don't you say that's the Wu language?
Well, as I said before, the term dialect in China, there's this old idea, right? That, what's the difference between a dialect and a language? Well, a dialect is a language with an army, right? So here, this isn't a well understood point, right? So they're called dialects because there is a conception that it's all one and the same language. Much of the same situation with Arabic, right? I mean, Arabic speakers, even though they speak languages which may actually be mutually unintelligible, think of themselves as all speaking Arabic because they have this common culture and heritage. From a linguistic point of view, had things been different, they're certainly linguistically as different as any of the Romance languages are from each other, or any of the Germanic languages are from each other. Had the political situation be different, it would be considered to be different languages, but the political situation is as it is, and then they're considered to be dialects. So, I mean, unfortunately, there's a huge amount of confusion in terminology, that surrounds all of this, which makes it very hard to understand what's really going on. But that's basically, Dan.
Yeah, just maybe to add one more clarification. If it wasn't for the political reasons, we would call this foreign accented Mandarin. But we can't call it foreign accented Mandarin because the people who are speaking it are Chinese, and in China, you can't use the word language to describe Shanghainese because it's politically not allowed.
And you certainly
So we
can't
have
use
to
the
call
word
it forward. No, we certainly can't use the word forward because languages and ethnicity are tied in China. So for political reasons, we have to call this Wu dialect Chinese. But in fact, this is foreign accented Mandarin, and the foreign language they're speaking happens to be one of the Chinese languages, Chinese.
But I assume that every language which we call dialect has honest to goodness dialects as well.
Yes.
Oh, yes.
Yes.
So Wu has many, there are many dialects of Wu. You go to Shanghai, you have one. You go to Suzhou, there's another dialect. You go, around Zhejiang province, you'll find many dialects. And, I'm not sure in the situation in Wu, but even, among those you may have dialects which are not mutually intelligible. Probably not in the case of Wu, I'm not sure. But in any case, it's, they are, full-fledged languages with their own dialects, which are, so. Exactly right.
Is there literature and are there writings in Wu?
Well, that's part of the reason that these are often not considered languages, because most of these, with the exception of Cantonese, which does have a literary tradition, most of these languages do not have any written tradition. I mean, it is, of course, possible in principle to write them, but people generally don't. So this is actually a problem in Taiwan where, a lot of Taiwanese speakers are trying to up the status of their language. Taiwanese, the southern end. And the problem is that there's no standard writing system for it. There's no standard way of writing it, and so they have to invent something. As I say, the situation is somewhat different in Cantonese because they do have a tradition of writing, and in fact you can actually buy Cantonese newspapers will have noticeably Cantonese vocabulary, noticeably Cantonese syntax in them. But that's the unusual situation. Most of these dialects, languages, whatever you want to call them, do not have a standard writing system. And that's always been true.
Why did you choose the Wu dialect?
Why did we choose the Wu dialect? I guess there wasn't. I actually don't know why Wu was chosen originally. Was it as opposed to all the others? Do you remember the particular?
I think it was the economic importance of Shanghai and the obvious choices were either Cantonese or Wu, and there had been some work on Cantonese and Wu hadn't been looked at, and it was it's the most important economic center.
But there's no linguistic reasons. I mean,
Okay, so, thank you. Everybody comes next, right? Come up.
Probably Giri does.
Okay.
Good morning, everyone. This is Giri Iyengar's
work for IBM Research, and I just wanted to introduce the team members. Sanjeev already mentioned Desislav and Matt, and Shaolei, Brock, Paul, and Paula for the grad students, and the senior research members are, and Dietrich, who's going to be a part-time member, and Manvata from UMass Amherst. Okay, so big picture. So part of you, some of you might remember this from the November when we presented this. So what we're after is that given a multimedia retrieval system, what we want to do is the system is presented with an information lead, such as finding clips of Yasser Arafat, and whoever is using the system might give an example to the system, which might be a picture. And the system has to go and retrieve it and come back and give clips like this, saying, which is a good match here. Right? And typically people that have built these systems have done it in two separate, completely distinct manners. One is purely text system, which runs either on the ASR, or on the pure text, so coming from closed captioning. And then they would do a pure text retrieval system using their either copy systems or the different kinds of text modeling. And then on the image side, a completely independent system which looks at the image features on the perceptual cues that come from the images and try to retrieve the same similar kinds of documents. And then what happens is that, which then ranks these two documents together, and then gives a final rank for each of the documents in your system. There are obvious problems with this, is that what happens if I make a mistake in the speech recognition, which happens all the time, or what happens if the particular image cue that is given to you is not like what is there in the image part of the system. Both of these systems are going to fail. And wouldn't it be better if you can have the text system give cues to the image system, saying that, oh, it's Yasser Arafat, it's a named entity, so it must have a face. Something even as simple as that. So you want to retrieve back documents which contain faces. You want to tell that to the image processing system. Likewise, you might want to tell something from the image side to the text side. Say that, expand the query in this particular way. Use these different words. So you might want to do things as simple as that. And what you really want to do is you want to use both the information both from the visual channel as well as from the text channel to model it efficiently. That's what we plan to do in this workshop. Right? So what we're going to do is we're going to expand the notion of a document having words and a query having words, and people doing language modeling based retrieval, which is very popular these days, and expand that notion to have a document comprising words and list terms. In a moment I'll define what I mean by list terms. And then having a query which comprises words and list terms, we want to retrieve the documents using that. That's what we want to do this day. Right? So what I'm going to talk about now is what do I mean by list terms, and then I'll walk you through one path to our system. One of the basic retrieval models, and how we can use ideas from machine translation, how we can use ideas from relevance modeling and hidden Markov models to help us handle these problems. And if time permits, I'll talk about what the task is and what the thought process to at the end of the presentation. Okay, so coming to list terms, right? Unlike speech recognition, where we have this nice fundamental unit called forms, which we can take the acoustics and then convert that into words, we haven't discovered something equivalent of that in computer vision yet. So we have to come up with our own vocabulary. And one common way to do that is to come up with a data-driven approach. So what you do is that you take these image features, like color, texture, what have you, and then run VQ, create your own vocabulary, and then use that to build objects and events and locations, what you find after. And when we do something like that, I'll call them as list terms, to give another similar analogy to forms. So let me walk you through one of them, right? So given an image as this, I want to extract the color histogram. I might want to extract color movements from them. I might want to run an edge detector through an image, and then extract edges, compute their orientations, and so forth. I might even run I might look at the gray level co-occurrences, and then compute statistics of these, matrices. Right? And here's an histogram. What I do is that I look at all the colors and then discount and plot, get an empirical PDF. These histograms can be estimated from the entire image, or you can just run a rectangular partition through the image and extract from different regions. And or you might even want to do is that you can take an image, run an automatic segmentation algorithm. This is, as an aside, it's running EM, fitting a full covariance Gaussian mixture to each of the image pixels, and then segments it that way. And you get these different regions, and you can extract features from each of these regions. These are different ways in which you can extract features. And then you go to quantize them to compute to get your list terms. Okay, so the different models that we're going to do is that given that we have queries and queries comprising words and lists and documents comprising words and lists, what you really want to do is you want to build a matrix such as that, which allows us to go from one to the other. Right? One thing that you can do is you can build a unigram language model, which is just computing how often a particular word or how often a particular wisdom occurs both in the document and the query. And obviously this still has the same problem that I mentioned before. I'm still modeling the two things fairly independently. The other thing that I can do is I can make it make the word system more complex, more elaborate, which is such as just as an approach is suggested by Berger and Lafferty, right? You can think of the query as a translate of the document, and then you can apply machine translation ideas. But yeah, I think they even fitted model 1 and model 2 to this particular problem. What we want to do is that we really want to translate between words and lists. So for this particular thing, we'll apply machine translation models, relevance models, and HMMs, and elaborate more as we go along. And likewise, we want to do the other counterpart. We want to convert the document words into query systems. We may be able to use similar ideas from these systems to build up models as well. Okay, so here's a little bit of math. Given a query comprising words and lists and document comprising words and lists, one approximation we may be able to do is assume that the word part of the query and the visual part of the query are independent given the document. And if you look at just one of those blocks, right, I may further approximate that by saying that I'm going to do a linear interpolation between the word part and the visual part. Right? So I'm delinking between the words and the visual part. So if I look at the highlighted block now, that's a fairly standard language modeling retrieval system that we're not familiar with. So I'll focus on this block, the different kinds of models that we can do for this block. So we have visual terms in the document, and we want to extract words to the query. So this is like a translation problem. One approach that people have done, including Pinar, who's part of the team here, is try different applications of IBM Model 1 and 2 for this particular problem. So here is a piece of work which looks at, this particular example, the tiger, looks at a large collection of images with their captions. And tries to run this automatic segmentation algorithm, the kind that I showed before, and then tries to label which part of the image represents the tiger and which part represents the grass. And I think it was an application of Model 1 for this particular problem. And you gets a reasonable result on this database. And you may argue that this is a fairly well-constructed, it's from an image side, it's a fairly simple database. But Pinar has tried this on a different kind of problem as well, where she's looked at the track width corpus, which is much more complex, which is like broadcast news data. And in this particular one was, I think, 1940s to 1970s kind of video, so it has a lot of image processing problems to deal with, a lot of noise and a lot of color artifacts that we had to deal with. And in that, running IBM Model 1, she's able to discover that Statue and Liberty are the top 1 to 3 words to annotate these particular keyframes, which is fairly good. And the other way you can think of this is that look at a large collection of training images using something called a relevance model. What it's trying to do is it's trying to build a joint model between words and wisdoms and using a training collection. So you might have a collection of, say, annotated images where you have the wisdoms extracted using your image processing, and you have words doing as captions. And what you want to do is you want to build a joint model for observing those words and wisdoms together. And here are some annotations which show some example annotations on the track with 2003 data, where Manmata had collections of images and annotations that go with it, human annotations that go with it. And when you train these relevance models on those, you get fairly nice looking annotations. And in fact, you can query, for example, the bottom, you show a query there, it says outdoor skies and transportation as the text query, and you get those following images back. Most of them have cars or ships, which are transportation, and it has skies and outdoors, all of them outdoor shots. It's a fairly good retriever. And here's another variation on this relevance model, where instead of having wisdoms, which are quantized, what we're doing is you can model them as continuous observations. So image features tend to be continuous, so why model them? Why discretize them? Why come up with the synthetic vocabulary? Let me start with the continuous observation. So I come up with a generative model. There's an image which generates words and it generates image regions. And image regions, you can model them as Gaussians. And then you can try to build these models. And when we deal with continuous features, we'll call this continuous relevance model. And the important thing to take from this chart here is that we can try these systems while they are tried on a small part of the data. They come out to be as competitive as the large system that people have built. The main difference is that this was tried on a small set of about 5,000 keyframes from TrekBuild, and most of the people who build these systems built on the order of 35,000 keyframes. And but the results in terms of the mean precision and recall are roughly comparable to what people get in terms of what other systems have built, including what IBM was built last year on the same corpus. So this particular approach is actually fairly competitive with these different specific modeling techniques. The other approach that we are planning to try is a standard HMM approach, where we're going to assume that each image region is an observation coming from an HMM, and the HMM has word states. So then what you can do is that the observation can be either continuous or discrete. We're going to try both of those. And we can use the standard, we have some labeled data for training, and we can then do bit-to-bit decoding to actually annotate these images and see the joint model between the words and the stuff. We're going to use the standard tools such as HDK to help us do this. Okay, so the corpus that we have is the TrekBuild corpus comes from ABC and CNN. It's part of the Hub4. It's not the entire Hub4 corpus. Plus, it has some extra CNN data as well. Sorry, C-SPAN data as well. And it's roughly 120 hours of video data. And we have the closed captioning for most of it. And Lindsay has provided us with the ASR for this particular corpus. And in addition, the development partition of the data has manual annotation. So NIST, as part of its activity last year, had a common annotation forum where on the order of about 100 people labeled this corpus with all the different concepts that are occurring in the images. So the development partition has manual annotation for those. And in addition, we have relevance judgments from NIST from 2003 for some of the benchmark concepts on which they evaluated last year, and all the query topics that were there. So that's going to be the corpus of the task that we have. And the kinds of evaluation that we're going to do are, one is an intrinsic evaluation where we look at how good the image annotation performance is. For that, depending upon which concepts we're evaluating, if it's the benchmark, we have the relevance judgments from NIST, so we can just use that. For the common annotation on the development data, we have all the human labels that we can use, and then we can compute different numbers such as the average precision, the mean average precision, and the precision at particular residual points, and then compare that with other systems that people have built for TrekBuild, which are purely based on the images, not on text. And on top of that, we will do an extrinsic evaluation where we look at essentially the retrieval performance of these things, of these three different models on the Trek 2003 topics, and again compare ourselves with other systems that are built on the same idea, other systems which are typically distinct speech systems or distinct image systems, and compare that with our joint modeling system and see how will we do with respect to this. So so just walk you through one path of the system, talk about what systems are, and then talk about the different kinds of retrieval and the translation models that we're going to try. So any questions at this point, I will gladly answer, or turn over to the appropriate person in the audience.
Davis from this area. I know that there's been some work in getting humans to label images using a game called Taboo online. I don't know whether that corpus would be useful.
I don't know how many people have played this game Taboo. It's a fairly nice game. You go onto a website, essentially, it gives you an image, and you end up doing image annotation without realizing, which is good. They're collecting training data for free, not even paying students to do it. So, but that data is fairly useful.
Could you describe it a little bit?
They show a whole bunch of images, and then they ask you, finally what you have is that you have a bunch of images, different kinds of images. For example, it could be from people's home collections and stuff like that, and annotations that go with it, saying that what is in the image. So each person, for example, you might see something different, and I might see something different in the image. You might write whatever is in the image.
Is there a control on the vocabulary?
What happens is you're paired with another player somewhere else in the world, and you have to try to guess what word they're using to label the image. So you guess, okay, this is apple, and they guess fruit, and those didn't agree. So you keep guessing words until you have a word in common. So this is a game that you're playing with somebody who you don't know. The only way you can you can communicate is by labeling the image, and you're not told anything until you both get the same word. So you're trying to guess what they would think of. So in the case of apple and fruit, it's too easy, right? So if everybody's labeling this image apple, then the word apple becomes taboo, and you're told you can't use that word. So this is a way of getting people to playing the game to generate additional labels for the image.
You can't use that word ever again, is that right? Or
for that
on this
particular image.
picture?
I think it's
For
that
this
particular-
picture,
Yeah.
yeah. So you're shown a picture, you're asked to come up with some labels for it, guessing how your partner is going to label it, and here's a list of 5 words that you're not allowed to use because they've already been used too many times before. So this is based on a game that you can actually buy in stores that I've played at parties. And they've taken it online and they're using it for image annotation. It's wonderful.
Yeah, so
Who's doing this?
I don't know. I don't know the particular image. Yeah, but yeah, the interesting thing is that because they force you to, at least 2 people to annotate using identical words, so that actually brings out a very interesting point, is that different people will have different levels of granularity at which they might annotate. And that's something that we haven't really understood. That's a very fairly well-known problem. In fact, there are people in Cornell who are the library science people who have done these kind of research, and they say that inter-annotator agreement in images is fairly low. It's on the order of 50% or 60%. It's very, of course, they've done it on the order of 1,000 images using about 10 or on the order of 10 subjects or so. So they're trying to scale it up to a bigger experiment, but that's about what they get. So it will be, yeah.
Oh, I had a different question. So all of the VIS terms that you talked about are actually fairly low-level image features, it seems. And for example, I know that in face detection, you can get people have found much higher accuracy by training the model specifically to look for faces in the image. Have you looked at using higher level?
That's true. In fact, yeah, one of the features that there is nothing in this particular model that prevents us from, for example, the wisdom could be a high-level detector. It could be a face detector. It could be some other semantic concept detector. Right? We just want a tokenized vocabulary. In fact, one of the features that we're going to do is actually use a face detector. But having said that, the beauty of these models is that they allow you to go between extremely low-level feature and these mid-level to high-level features in one common framework. That's what makes these models very appealing. But face detection is a fairly well-studied problem. There are probably on the order of dozens of PhD theses which have looked at face detectors. And people have done amazing things with them. We all have them. Faces have this golden proportions to them, which is very well exploited. So, how many of you are familiar with golden proportion? So it's the 1.618 number. So it's all human. Pretty much everything that you see in nature has this proportion to it. And even that is exploited. When people build face filters, they exploit those kind of things.
So you can actually extract semantic features from the face, or you can extract.
Or you can even do simple things as does this image contain a face or not, right? You can say, oh, it contains one face. For example, if I'm interested in queries of Yasser Arafat, we might say, yeah, the thing might learn is that it might attach itself to that stuff. So if you want to differentiate between Mark's face and Giri's face, you might want to do that.
How about texture features, things like stripes or sail?
We have textual features. We're using gray level co-occurrence matrices, one of those, and we have looked at Gabor filters. We're starting with a vector feature that's based on the kinds of questions that we get on the track, with objects or people or specific objects or specific people mainly as the question. So based on that, we came up with these set of features. But we can try other textual features as well easily.
Okay, thank you. I want to see what our situation here is from the time point of view. So, I see. All right, well, we can go on. I thought we might take a break now, but we're now where? We're now 10:40 and we're way ahead. Well, all right. So, who's talking? Yes, you are. So, Mark. And then we'll have a break.
This is our team, landmark-based speech recognition. We have faculty from University of Washington, Berkeley, DARPA, and SRI, and we have students from around the country, including some students who will be here all summer and some students who are in fact participating remotely because they're interested in the project. The goals of the workshop, really we're focusing primarily on two aspects of what's traditionally called the acoustic modeling problem in speech recognition, and we've actually broken that into two pieces. One could be called acoustic modeling, meaning specifically looking at the relationship between phone distinctions and acoustic observations, spectral observations measured in the signal. And the other looking at something that could be called lexical modeling or pronunciation modeling, and that is looking at the relationship between the phones with which a word is supposed to be pronounced, according to the dictionary, and the phones with which it's actually pronounced in spontaneous speech. And those two things are often quite different. And then we're evaluating our work because we need to have some, because there's been a lot of work on these subjects in the past 50 years or more. We need to have some sort of a fairly strict evaluation, and so our evaluation is actually doing a lattice rescoring task on the DARPA ears lattices generated by SRI and by BBM. Here's a quick overview of the structure that we're trying to build. The data actually starts from the lower left and upper right corners of this slide and works its way toward the lower right corner. We start first of all by running a series of support vector machines to detect and to classify landmarks in the signal, where landmarks are defined in practice as consonant releases, consonant closures, and syllable nuclei. We then try to detect those landmarks and classify them, both using soft decision frameworks for both of those tasks. At the other end, we start with lattices that have been previously generated by using a first-pass recognition system, and those lattices provide a series of word hypotheses that are time-aligned. They tell us what is the proposed start time and end time for each of the words that we're trying to match to the signal. And then we have a pronunciation model that tries to match those word hypotheses against the phoneme probabilities that are being generated from the signal. So here's a brief outline of my talk. The scientific goals of the workshop, let me just go through the talk rather than stopping to spend time on the outline. The scientific goals of the workshop really are, as I said, acoustic models to learn the most precise but at the same time generalizable models that we can of the relationship between the acoustics and each distinctive feature, to represent a large number of pronunciation variants, but in a controlled way. The task of pronunciation modeling is typically done by listing multiple entries in a dictionary, but people have found that if you list more than about 1.5 entries per word, there are too many options available, and so it adds to the confusion of the recognizer rather than reducing the confusion of the recognizer. So we want to increase the number of variants of each word, but we want to increase it in a controlled way and in a context-dependent way. And finally, our technological goal then is a rescoring task that reduces word error rate of the speech recognizer. The resources that we have include speech data. Right now we're working with 6 to 8 corpora, depending on how you count it. We're working with NTIMIT and with the ICSI transcribed subset of Switchboard, because those have manual phoneme transcriptions, which are extremely useful for training these support vector machines. We're working with a rather larger subset of Switchboard 1. And then finally we have 3 development test and evaluation corpora. The 2001 evaluation corpus we're using for development test. The RTO3 development test corpus we're also using for development test, and then the RTO3 evaluation corpus will be our final evaluation corpus. I'll come back and talk about the word lattices later on. The data that we've generated for these include a long list of acoustic features, and this is one of the key points that I hope to focus on is how we can include information from a much richer set of acoustic observations than the standard 39-dimensional MFCC plus delta deltas. So we're starting out with MFCCs because they're the standard speech recognition features, but we're starting with 2 different window sizes. A 5 millisecond skip with a 25 millisecond window is the standard that's used in most speech recognition systems. A 1 millisecond skip with a 4 millisecond window is really a very coarse sort of representation, but it's observed very, very often. And basically it gives us information like the energy once per millisecond and the spectral tilt once per millisecond. We're looking at two different measurements of formant frequencies. One is computed using a standard LPC-based analysis. Another is computed using a mixture of LPC and SVD signal subspectrum-based analysis. And then finally we have, well, actually not finally, but then we have some knowledge-based acoustic parameters, and finally we have two auditory models that we're generating using to generate acoustic features. One is some features that Shihab Sharma has developed in the past 2 or 3 years, and another is Stephanie Seneff's auditory model, which is somewhat older. I've mentioned distinctive features. Distinctive features, phonological distinctive features, distinctions among phonemes are a topic of tremendous contention among linguists. I'm trying to sidestep most of that contention. To me, a distinctive feature is any binary partition of the set of possible phonemes. So we're looking at any way of taking all of the phoneme distinctions that you want to make and cutting it up into a binary distinction. We're looking at, in particular, two different kinds of distinctive features. One is sometimes called an articulator-free feature. It's sometimes called a manner feature. These are things like, is it a stop or is it a vowel? Is it a stop or is it a nasal consonant? The manner features that we're looking at right now are speech versus silence, which we're calling a manner feature. Consonantal versus non-consonantal, continuant, sonorant, and syllabic. And then all of the other features. Place of articulation, things like is it made with the tongue blade versus the lips. Voicing, which is only salient for fricatives and stops. Is it voiced or is it unvoiced? And the driving force really originally behind using support vector machines is that the information about, for example, the distinction between something made with the lips like a P and something made with the tongue blade like a T is, for a stop consonant, is encoded in a relatively complicated pattern of spectral change over a long period of time. These are 150 millisecond spectrogram chunks, and you can see that in general, at the T release, you have a lot more energy in the high frequencies right at the burst of the T than you would at the burst of the P. And then you also have a different pattern of change of the spectrum over time moving into the vowel. That phoneticians would describe this by saying that F3 of the T comes down as you move into the vowel, whereas all of the formants of the P rise in frequency as you move into the vowel. So the problem becomes then, how do you learn from a 1,000-dimensional observation vector or a 2,000 or 3,000-dimensional observation vector? And I apologize that I don't have all the same kind of plot here, but this is really one of the motivating principles behind what we're doing. These are two. The left column and the right column are two different classifiers trained to classify lips versus non-lip stop releases. That is P and V versus all other kinds of stop releases. Both of them are trained using an observation that's a 1,000-dimensional observation. It's a complete spectrogram. So we're taking a classifier and we're giving it a 1,000-dimensional observation and asking it to try to make this binary distinction. Using standard techniques, this actually, you get the same result whether you train the recognizer to minimize error on the training corpus or using linear discriminant analysis. You get perfect separation of those two categories on the training data, and you get no separation at all at chance on the test data, right? You have basically you have a 1,000-dimensional classifier. It's hard to generalize a 1,000-dimensional classifier from training data to test data. There's recent developments in machine learning. So I guess in the past 10 years or so, have led to a series of what are called regularized learners that rather than trying to minimize error on the training corpus, they minimize an error metric that includes the training corpus error plus some estimate of how badly will be the generalization from training corpus to test corpus. So in effect, you're trying to minimize the expected error on a test corpus that you've never seen before. And you're minimizing it using an upper bound on what that error might be. Here's the resulting classifier that you get training a support vector machine on the training data. And although it's not as good on the training data as the minimum error technique, it generalizes to the test data. And here's a histogram of the discriminant on the training data and of the discriminant on the test data. The error on the training data is 13%. The error on the test data is 18%. So it's by controlling this upper bound on the generalization error, you've learned a classifier that's able to generalize from this 1,000-dimensional observation. All right. So what we've done for the corpora that we're working with is to train a series of so far about 33 support vector machines, and then to map those output discriminants into posterior probabilities. One of the problems is how do you take this discriminant and then include it into a framework that'll do more than just binary classification. So we generate output posterior probabilities. Here are a set of 10 of those posterior probabilities for this particular waveform. And these probabilities are firing in a, so these are probabilities are between 0 and 1 for the probability that this particular place in time is, for example, a plus minus consonantal, a consonant release, basically. And most of the time these probabilities are going toward 1 at the right place, but they're also rather noisy because they're doing a binary classification once per frame. And I'll talk in a little bit about how, I'll come back to how we smooth that. Another thing that I've done is to just, we need some kind of lexicon coded in these terms, and so I've written some Perl scripts that will parse the switchboard and call home dictionaries in order to generate distinctive feature lexicons. All right, how do we smooth the outputs of those support vector machines? We have two techniques that can be run in series, actually. The first technique is a dynamic programming smoothing algorithm that essentially tries to maximize over the entire signal the probability that you have a particular kind of consonant release at a particular time, multiplied by the probability that you have a particular delay between that consonant release and the next consonant closure. So it's a Bayesian product, a fairly standard kind of Bayesian product, kind of upside down, I guess, from the hidden Markov model, but not too different from what you might call a stochastic segment model. And that dynamic programming smoothing can result in much better results. This we have running in two different methods. One is already a word lattice rescoring system. It computes those probabilities with the constraint that the series of landmarks has to match the series of landmarks proposed for the word in the lattice. The other is an unconstrained DP smoothing that basically is a manner class segment recognizer. It says we don't know in advance what the phonemes are in this section of speech. Just find the most likely sequence of landmarks and smooth the SVM outputs in that way. The second smoothing mechanism, which actually is a rather more general system, is a dynamic Bayesian network model that models pronunciation variable in continuous speech. And the problem here is that even though the word everybody is canonically has 4 syllables and is pronounced with a V closure followed by a B closure followed by a D closure, and here we have closures of the lips close for the V, they close again for the B. In between we have a tongue blade glide, and we have a tongue blade complete closure. Even though that's the canonical pronunciation, that's very unlikely to be the way somebody actually pronounces it in conversational speech on the telephone. Here's an actual, one way in which somebody has actually pronounced it on the telephone is to say everybody. Everybody can be pronounced everybody. And the representation that, so you can't, if you go and include everything like everybody in your dictionary, if you go and include 35 possible pronunciation variants for the word everybody in your dictionary, then you'll wind up calling every section of speech the word everybody. Because there's no distinction between one word and another word. The word everybody could be everybody, the word every might be everybody, the word that body might become everybody. There's no distinction between one word and another. So we need to find some way of representing the distinctions between one word and another, while at the same time allowing the flexibility to recognize the pronunciations that actually occur. And the way that we're doing that is to represent separately the different articulators. For example, the lips may, instead of having this very detailed representation, the lips move rather slowly, and so the lips might actually just move into a glide at the beginning of the word and then move out of the glide at the end of the word, and they might not have a complete closure anywhere, and they might not constrict to a fricative and then release again, and then constrict and then release again. They might just have a glide all the way through the word. And then the tongue blade is fairly quick, so the tongue blade can go ahead and produce its glide and then produce its complete closure. The tongue body is also pretty slow, so the tongue body might not open up to say the sound aw. It might just stay roughly open during the entire word. And the result is something that sounds a lot like everybody. The only thing that's moved in there is the tongue blade. The representation for this variability is a dynamic Bayesian network that looks like this. Let's see, what can I describe quickly? We have a word and the relation, and then we have each of the, here are three different articulators, say for example the tongue, the lips, the tongue blade, and the tongue body. Those three different articulators have, for each of them, three variables. They have an index that says which of the phonemes in the word am I looking at right now. They have, from that is generated U sub t of that articulator, which is the underlying correct form of the closure for that articulator. And then from that is generated S sub t of that articulator, which is the actual observed surface form of that articulator. And the other variables there control the synchronization between those articulators. Those articulators can get a little bit, two things can happen. They can get out of sync with one another, generating pronunciation variability that way, or they can be reduced, meaning that a full closure might not be implemented as a full closure. It might just be implemented as a glide closure or partial closure. All right. To do the actual lattice rescoring or NBEST rescoring, we're using primarily SRI language, the SRI language model toolkit. And the general idea is that we'll integrate these novel scores with the existing acoustic model and language model scores using a weighted sum of log probabilities. The lattices that we have been contributed by Andreas Stolke at SRI and by Owen Kimball and Spiros Matsoukas at BBN. We have lattices for the Rich Text 2003 DARPA competition, and we have lattices for the 2001 switchboard evaluation. And here's a little bit of analysis of the kinds of things that happen in those lattices. We discovered that most of the errors in the lattice seem to be function word substitutions. In fact, 6 of the top 8 are function word substitutions. The kinds of errors that we get in terms of the phonemes involved seem to be primarily consonant confusions. In fact, more often onset consonant confusions than coded consonant confusions, but that depends a little bit on which set of lattices you're looking at. I think that in the BBN lattices we had more coded than onset.
I mean, these are results not employing your technology.
Right.
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 So these are the base.
These are the baseline.
These are,
Bill?
And this is an analysis of the one best or of the lattices?
This is an analysis of the one best. And just to give us an idea of where we stand, we did last week, and I guess we could call it week 0, we did a lattice rescoring experiment. We did unconstrained smoothing of the SVM outputs using one that's event-based dynamic programming system. We then integrated those into the DBN system in order to allow asynchrony of constrictions, but not reduction of constrictions. That is, we can't go from stop to glide, but we can allow 2 different articulators to be asynchronous, and that's for computational reasons that I'll come back to in a minute. Used those to compute a new SVM DBN score for each word in the lattice, added those to the existing language model and acoustic scores. So we basically put a new annotation onto each edge in the lattice. And because we haven't re-estimated stream weights yet, we've kept all of the stream weights exactly the same as they were in the original lattice scoring pass, and we just set the stream weight for this new score to be 1.0. That is, it has the same weight as the original HMM-based acoustic score. And here's one lattice. Here's one lattice on which we got a word error rate improvement. In fact, for computational reasons that I'll talk about again on the next slide, we've done this for exactly one lattice. And here it is. We get a word error rate improvement. Perhaps more interesting to me, I guess, considering this is just one lattice, is to look at exactly what kinds of improvements and what kinds of problems we have so far. The SVM does, in fact, seem to improve our ability to find out how many syllables there are in the sentence. It does, in fact, seem to improve our recognition of the place of articulation, in particular of consonants. It improves our recognition of consonants. The SVM currently has no model of vowels, so if I run this with the SVM only without including the HMM scores, then we get pretty bad performance with vowels. And in this case, so far, we have a nice one lattice, one word improvement, which is not yet anything to write home about. All right, so the things that we need to work on are, first of all, how best to combine the language model and the acoustic model and VBN model scores. Second, perhaps we need to work on computational complexity. Rescoring that one lattice took 2 hours. So for 2,000 lattices, that'll take about 4,000 hours of CPU time. So we need to work on methods of controlling computational complexity. In particular, it would be nice to include flexibility such as to allow stop-to-glide reductions. And finally, something that I was more concerned about until I saw this result, but I'm still concerned about, is that the SVMs are not still, they're doing binary classifications and they're doing manner classifications and so on considerably better than a mixed or Gaussian model would do on the same task, or than a simple HMM would do on the same task, but they're still not anywhere close to the performance of human listeners, and we need to find out if the current performance is good enough for our system.
So when you say human listeners, do you mean given what kind of context?
Given the same context that the SVM is using, given 150 milliseconds excise from the waveform. So,
how well do human listeners do?
Actually, you've done this more recently than I did, and you found that the human listener did worse than the SVM, right? Human listeners do anywhere between, so given a clearly articulated nonsense syllable, human listeners make about 1.5%, get about a 1.5% error rate on that. Given data from conversational speech, with all of the variability that implies, the human listener performance is, I think, above 15%. The human listener error is above 15%. You've had 18%?
I had like 28%.
Oh, was it really? Okay. I think that I've had
What
less
is
than
the
that.
task?
The task is to play back 150 millisecond waveform chunks excised from conversational telephone speech and to say what the constant was in the middle.
What the constant?
Yeah. Yeah.
It's a little artificial
then,
because of the shortness of the...
Yes, it's artificial for the human listeners. Right. I think that...
Okay, so, excuse me, in one case these were nonsense syllables, and in another case this is excised from switchboard or something like that?
Right. If
or
it's
Fisher or whatever.
Yeah. Yes. If it's nonsense syllables, human listeners do very well because...
No, but I'm just wondering how it's done.
Right.
So
excise from switchboard.
There is no attempt to make it difficult. You just at random select the boundary, at random you select the other, well, maybe you fix what the interval ought to be, so you select one boundary, etc., and then you present.
Right. Exactly.
And how should, there may not be a consonant there at all, right?
Oh, we selected around a randomly chosen consonant.
I see. So you choose a consonant, and then you choose the previous boundary at random with some.
Yeah, we choose a consonant at random from the entire corpus, pick the release of that consonant, go back 75 milliseconds, go forward 75 milliseconds, and excise that waveform, and play that waveform to the listener.
I see. Okay.
And I guess...
so what's the result?
So the result... the most recent...
Humans do what?
The most recent result, actually, is that humans do get 28% error on that task.
And the machine?
The machine gets, let's see, which feature was that?
That was lips.
That was lips. Machines are getting about 25% error on that task now. Our best SVMs are down to about 25% on that task. So maybe my last bullet point is not valid anymore. Maybe we've passed human performance.
It wasn't a very carefully controlled experiment.
Okay.
I mean, it's really hard because of the artificiality. What you'd really like is to get spontaneous nonsense speech or something like that.
Yes. Yeah. Yeah.
What's artificial about if it's done the way Mark described? You just said it's artificial. I'm asking you.
Yeah, because your language processing device isn't trained on 150 millisecond snippets of speech. The way the SVM is, yeah. You might be very good at doing it, if you had a little bit of run up to prepare you and run off or something like that. It may just be that you are only good at getting the phonemes in the middle of some longer string of speech.
So we got to follow up the SVM somewhat. I mean, We're too good to the SVM. It's not that the humans should not be able to do that, but that the SVM should not be told ahead of time.
Shouldn't be told ahead of time exactly how much speech is going to be seen.
Yes, exactly.
Yeah. Well, I mean, there's two ways to fix it, right? One is to foul up the human, and the other is to, I'm sorry, one is to make things easier for the human by making it a more natural task, and the other is to give the SVM the same advantages that a human would have by adding a language model, which in fact is part of the project itself.
Okay.
Yeah. All right. So, so given that those are the problems, well, our schedule really is the first thing we want to do is to try more lattices. We have the SVM scores for 20 lattices, and hopefully by tomorrow we'll have lattice rescoring results for 20 lattices. Sometime by about a week from now, we want to basically automate to some extent this process of generating word scores for a large set of for the 36 conversations in the development test corpus, and then automate to do some stream weight training, perhaps on at-best lists, and then do a complete rescoring experiment for the RTO3 development set. We also want to train SVMs using all of the acoustic observations that we have. Right now we have them trained using a subset of those observations. And then we have targets August 7th to have everything in place for our final evaluation experiment, and August 10th to actually have our final evaluation experiment performed so that we can do a little bit of post-hoc analysis prior to the final presentation. So in summary, there are two problems that we're focusing on. One is how to use a very, very rich set of acoustic observations in order to study the relationship between the acoustics and the distinctive features. In a sense, you could, although we started out thinking in terms of binary distinctive features, a lot of things have led us to constrain the problem to binary distinctive features. You could say that it's constrained to that because the best performing regularized learners currently available are for binary distinctions. The binary support vector machines tend to perform better than multi-class support vector machines. The other problem that we want to look at is the problem of increasing the flexibility of the pronunciation model without overgeneralizing or overgenerating pronunciation variants. That is, to generate variants in a controlled way, in a context-dependent way. And we want to do those for a lattice rescoring class. That's all I have. Any questions?
So one thing I couldn't work out quickly enough from your description of the DBN is whether you're modeling the inertia of the articulators.
No, not currently.
No, okay.
Well, so actually, yes, in a sense, there's a transition probability from one degree of closure to another. The degrees of closure are highly quantized. There's completely closed, fricative closure, glide closure, regular open, and wide open, basically. And it's more like the articulator may learn that it has a higher probability of moving from a regular opening to a glide opening than of moving from a regular opening to a full closure. But in fact,
right, but it's not going to give you something like a Sagasaki targets model.
No, no, it has no complete model of dynamics like that, no continuous model. Other questions?
About your feature, front-end feature extraction procedure. You're using the same standard MFCC feature like spectral processing, fixed frame size. Do you think it's a little bit like outdated and suboptimal? Have you ever heard of about the chaotic nonlinear features from the chaos theory and some other new methods doing like front-end feature extraction? And another question, do you think that the future front-end feature extraction for speech recognition will have to be speech synchronous?
Let me answer the first question first because there's a more certain answer, and that is that we're trying specifically to include a much, much richer set of acoustic observations than the standard MFCCs. We're including, our set of observations right now include what you could call spectral observations, phonetic observations, and auditory observations. The spectral observations are MFCCs because we need to some sort of compression of the FFT spectrum, but their MFCC is computed with two very different sets of parameters. One is basic, with a 1 millisecond skip and a 4 millisecond window, we're looking basically at the energy once per millisecond. With a 5 millisecond skip and a 25 millisecond window, we're looking at the spectrum the same way that a standard recognizer does. The phonetic parameters include the formant frequencies, and they also include some timing parameters such as the subband aperiodicity of the signal, the aperiodicity in different subbands of the signal, and other knowledge-based measurements that look at relationships among spectral energies. And then finally, the auditory modeling measures are based on two different auditory models. CNF's auditory model includes the mean rate and synchrony in a number of critical bands. Shamma's rate place model actually looks at the rate. I think it looks primarily at the rate of change of the center frequency within a subband over time. So it's in effect it's a set of chirp detectors, kind of a set of Gabor filter measurements. These, in theory, I think that this representation is set up to look at any acoustic features that you could throw at it. And I would like to look at even more features than this, but we've had to select some that we're going to focus on for the summer, and these are the ones that we've been able to come up with so far.
Actually, James Gardner said something like, in order for speech processing to move forward, we have to drop FFT. How do you think about
this? Yes and no. So let me say what our results are so far. Our results are so far that we can get tremendous improvements by adding other features to the FFT-based measurements. But usually when we drop the FFT-based measurements and instead use other features, usually we get a performance drop. So I think that the FFT-based features are still getting something that so far we haven't been able to get with the other observations.
About the second part of the question, speech from them.
That's a really interesting idea, and I haven't thought about it at all.
It's an old idea.
Yeah. Yeah. It's a good idea. I haven't thought about it.
Any other question from anybody else? Yes.
Yes. When you train your SVM, you need a training set. So you need to build it, and can you build it such that it's really perfect, that you know exactly the class, or do you have some errors here? And you take it into account after all?
We take it into account currently in two ways. We're training the SVMs, so far we're getting better performance if we train the SVMs using manual transcriptions. That's why we're using the NTIMIT corpus and the ICSI corpus. And second, there are still some errors in the manual transcriptions, and so the SVM training procedure we're using actually discards a certain number of outliers, discards extreme outliers before settling on the final SVM. So in addition to, the SVM has a built-in mechanism for ignoring errors that are above a certain threshold, but you can also, if it's too far beyond that threshold, you can actually discard those outliers before settling on the final classification boundary. And I'm not sure if those two are sufficient to solve the problem of incorrectly labeled data or not, but that's what we have so far.
All right. Now we have a break, but we're 15 minutes. No, we're what? 15 minutes ahead, 20 minutes ahead. So I don't know. We ought to take advantage of that. Maybe 11:05 we should be in Schaefer 100, which is one flight up, and there'll be all sorts of talk. Here, of course, is scheduled a 10-minute lunch, so we don't want to push you that far. I think that's an error. It should be 1:25 from 11:55 but who knows when we're going to end. I mean, I think we're going to end much earlier. Anyway, there'll be team meetings, and we have reserved certain rooms for you.
Fred, move away from the screen.
Oh, good idea.
You
All
also
right.
project the shadow.
Oh, well, right. So I will point out that this is wrong, and these times all of them will be wrong because we're ahead of schedule, but this is going to be correct. And I think we'd like to have a steering committee meeting at the end of it. Where do you, what rooms?
We'll have a room probably in Clark Hall for the steering committee meeting this afternoon.
Does everybody know where Clark Hall and all that stuff is?
Why don't we do this? I'll gather the people who need to be for the steering committee meeting, and I'll take you there to Clark Hall.
Yes, so shall we have it at 3 o'clock?
3 will work. Team leaders, do you think 1:30 to 3 is enough for the initial team meeting?
Well, it'll have to be.
Okay, 3
Okay,
o'clock.
3 o'clock steering committee meeting. So now I have 10:50. So let's have a 10-minute break, and then at 11 we're going to gather in room 100, Schaefer 100 for additional instructions. Right.